자, 조금 이르지만 먼저 출석을 불러보도록 하겠습니다. 이재혁 씨, 오한우 씨, 신준호 씨, 이승빈 씨, 그리고 이정재 씨, 이충아 씨, 정상아 씨, 그리고 홍규표 씨. 김민선 씨, 김유신 씨, 배민현 씨, 배서령 씨, 서하연 씨, 그리고 조대현 씨, 최승주 씨, 김성수 씨, 오셨고, 미스터 마니케르 아직 9시가 안 되었으니 조금 더 기다리도록 하죠. 네, 시작하기 전에 질문 있으시면 지금 하셔도 되고요. 네.
트라이어드 모드에서 볼티지 개인이 존재할 수 없나요?
볼티지 개인이 존재할 수 없냐고요?
있는지.
네, 물론 있죠. 물론 있고, 그렇지만 세츄레이션 모드일 때마다 개인이 적을 수밖에 없고, 그래서 안 쓰는 것뿐입니다. 그래서 개인을 우리는 사실 지금 얘기하기로는 맥시마이즈 하고 싶다고 얘기를 하고요. 근데 나중에 되면은 사실 개인 자체를 개인만이 유일한 뭐라고 할까요? 유일한 성능 지표는 아니에요. 그런데 우리가 나중에 하게 되는 것들은, 나중이라는 건 이 과목은 아니고 다른 과목에서 더 후속 과목에서 하게 되는 건 개인을 포기하면서 대신 다른 성능 지표들을 높일 수가 있어요. 그러니까 보통의 우리가 엔지니어링에서 보게 되는 많은 문제들이 어떤 하나의 성능 지표를 최고로 높이는 것이 문제가 아니라 여러 가지 성능 지표를 동시에 만족시키는 걸 목표로 하게 되는데, 그런 일을 하게 될 때 우리가 생각을 해줘야 되는 게, 만약에 우리가 모든 걸 다 포기하고 하나만을 최적화를 하기를 했을 때, 그때 그것을 가장 높게 만들 수 있는 조건을 잡으면, 그리고는 그거를 희생을 하는 거예요. 그리고 나서 다른 것들을 더 높여줄 수가 있습니다. 예를 들어서 트라이오드 모드하고 세츄레이션 모드로 동작할 수 있을 때 만약에 우리가 그것을 세츄레이션 모드로 동작을 시킨다면 동일한 게이트 바이어스 조건에서 더 높은 게인을 얻을 수 있겠죠. 근데 그거를 나중에 뭔가를 희생을 할 때 원래부터 게인이 높았으면 거기서 줄어들더라도 다른 곳에 쏟을 수 있는 여력이 있는 겁니다. 그래서 사람들이 또 거의 그러니까 뭐냐면 이렇게 생각을 해주시면 돼요. 거의 이걸 생각을 하실 때 모스펫을 세츄레이션 모드에 놓지 않고 트라이 모드에서 동작을 시키는 경우는 앰플리파이어에는 없다라고 생각을 하시고 작업을 해주시면 될 것 같습니다. 좋은 질문인 것 같고요. Okay, so time is up now. It is 9:01. I will check your attendance once again. So 최승규 씨 오셨나요? 김성수 씨? 미스터 마니케르? 오케이. So, okay. We are in lecture 21st. First of all, welcome back to the classroom. So we had a difficult time to to get back to the online lecture. So I remember that you have two online lectures in previous lectures, and now we are here as once again offline lecture. Okay, so we are in lecture 21st, and I guess that we will have 6 more lectures including today's lecture. So I think that starting from today's lecture, maybe we will continue similar discussions up to lecture 23rd. After that, we will have 3 more lectures. So those lectures will be devoted to the discussion about digital circuits. So you know that currently we are working with a category of circuits, sub-circuits called amplifiers. Our goal is to amplify small signal input to, although still small, but magnified version of those inputs. So that was, or that will be our discussion. So we will continue the discussion about amplifier. After that, maybe 3 or 2 lecture hours will be devoted to the digital part. Of course, if you are interested with the digital circuit design, then you have to proceed to the more advanced courses. So, so I think that there are 2 ways. Here we have amplifiers. This is kind of analog circuit, and there will be digital part. So in our college, you will find in 4th semester 2 different classes for circuit related topic. One is yes, so this is the second lecture of our microelectronics, and there will be another one which will be devoted to the digital design, digital circuit. So if you are interested, I want to recommend you to attend those lectures depending on your study interest. Okay. So anyway, let's come back to our discussion about amplifier. So we have plenty of concepts to be discussed in today's lecture and remaining lectures. So we will cover those concepts, but still, I believe that it is more important to me is make all of you understand basic philosophy inside this lecture. That is not my intention to proceed the lecture, so we can reach far more if I'm going to faster. However, instead of that, I wanted to once again ask you, if you have any question or any unclear part, then please let me know. It is more important to me to make you understand. Any question? If you don't have any question, so I will proceed. However, whenever you have question, please interrupt me, or you can send me an email. Still, some of you are sending me emails, so some of you are not sending me emails, but I think that the guy who, or the students who are sending me emails will get much more than others. Okay. Okay. So any question? If not, then please let's go to review of our previous two lectures. The main concept is like this. By combining our simple two circuit elements called an MOSFET and a resistor, we have achieved very important characteristics between input voltage and output voltage. Maybe you remember the circuit schematic. Yes. So we have one single resistor, and here we have an MOSFET. And say that this gate voltage is regarded as input voltage of this sub-circuit, and we have here output voltage taken from the drain voltage of our MOSFET, or under some resistor voltage not connected to the VDD. So now you understand it has the property looks like this. Yes, here we have input and output characteristics. Then how does it look like? So as you can see here, sorry. Yeah. I think that. Okay. So I'm a little bit confused because I'm using currently two different writing programs in my lectures. Okay, sorry about that. So here we have 2 points corresponding to input is corresponding to logical 0 or logical high or logical 1, and in between we have a smooth transition. However, that smooth transition just looks like this. So up to our threshold voltage, the output is just fixed to the VDD. Yes, this is a VDD. After that, we have steep decrease of our output voltage. Yes. So there is something like this. So if we are interested with digital application, then our input will be either 0 or VDD. And also, we will recognize only the voltage close to 0 or VDD. So, simply speaking, we can say that this system just looks like this or that. So when you insert the voltage close to 0, then you will have the voltage close to VDD. Also, when you insert the voltage close to VDD, then you will get the voltage close to 0. Not exactly 0. You know that in your previous homework, you have calculated the non-zero value appearing here. But anyway, that is quite close to 0. So we can think that this sub-circuit as an realization of an inverter, logical inverter, logical not gate. When you insert 0, it gives you 1. When you give 1, it gives you 0. So just inversion, logical inversion in this case. But currently, we are not talking about this digital domain thing. And where are we now? Instead of that, our input is not like this, either 0 or either 1. Instead of that, our input is just superimposed into certain DC bias conditions. So it means that here, let's say that we will use it as a operating condition for our signal. this is just the operational condition, and when we just insert V in its DC value, it does not contain any information. This is just a basic requirement for operating of our amplifier. The signal is added as term of a small signal, time dependent signal, and when you insert a small perturbation here, for example, as time elapses, if you have this kind of variation of your input voltage, and depending on the shape of your voltage transfer curve shown here, then you will have either higher voltage or lower voltage, and that will occur as variation of your output voltage. So you will just take this time dependent variation of your output as what? As output signal of your input voltage. Of course, this variation is regarded as a signal. However, it also contains what? It contains also just operating conditions. So you have to say, here we have V out and it's a DC bias condition. However, from the viewpoint of our signal transfer, we always think that this contains signal and this contains signal. Sometimes we forget about the importance of this guy and that guy. However, please note that if we do not provide sufficiently good optimal value for our input voltage and output voltage, their DC values, this amplifier okay, let's check whether my tablet is still working or not. Okay, at least okay. Okay, so it is important to have a proper working bias conditions. So at the end of our previous lecture, I told you that in order to support those working bias conditions, we have to introduce a certain additional circuitry for input voltage. Do you remember? For example, this bias condition is not either 0 or VDD. So this is not directly available from your circuit. So you have to generate the bias condition you wanted to have. So in front of your core part, so this core means that here MOSFET and resistor part, you have to introduce something here. Something means that, yes, here we have something to provide certain DC bias condition. So you remember it. So how was our approach at the time? I remember that we just extend our VDD here and ground here, and just to introduce certain serially connected resistors that can provide us a certain voltage division. Okay, so now we can select the value of our DC input voltage quite easily. That was the end of our previous lecture. Do you have any question about my explanation? So if you don't remember, then please let me know. And I remember that we have thought about the quantity called gain. So yes, so we have thought about gain. At the time I just wrote gain, but it usually has a symbol like A, so voltage gain. And that was defined as the ratio between our output signal and input signal. Oh, please have a look at this part. Here and there, we are now showing just small letter V and small letter V here. Of course, if we just observe the output voltage, it's not exactly the output voltage. Output voltage itself is just regarded as VDC plus V out. That will be the real output. However, you know that still we believe that this DC operation condition is regarded as just a granted one. So we do not care about DC bias one. So it is always there and we will not treat it as a signal. So that's the reason why, although in a circuit, although we have always the DC bias values for both of input voltage and output voltage, but we just take only small signal part. That is one point. Of course, here and there we have V in and V out. However, they are just a time varying signal, and just taking them in this way is not very good. So we have to care about their base component. But anyway, so I mean that simply speaking, we just take the amplitude of V out and amplitude of V in, and that will give us the ratio called voltage gain. Okay? So that was already discussed in our previous lecture. So if you have any question, then please let me know. So now I wanted to start our lecture today from a little bit more about the biasing circuitry. So we say that here we have a VD. And here we have ground line. So in order to provide a certain input voltage, we have introduced a pair of resistors which are serially connected. For example, let's say R1 or R2, whatever, R1 and R2, and then what will be this output voltage, or sorry, not output voltage, in this case that is actually used for DC input voltage. And anyway, what will be the voltage? That is simply given by VDD times R1, R2, R1. Do you have any question about this simple division rule? So maybe not. So this is so simple. So you can, but just changing your ratio between R1 and R2, you can immediately select the operating condition, and that will be used as your V in this system. Up to now, everything is quite simple and straightforward. However, please note that what is your ideal purpose? We wanted to impose our gate as this one, V in DC plus our input signal. So today we will talk about how can we impose this input signal, small signal input, into our circuitry. Yes, so if this is the case, maybe some of you think in this way. Oh, okay, we have already this part. Then why don't we just insert in this way? For example, here we insert small signal input corresponding to the in T and R1 and grounded. So then what will happen to our system? Do you think that this is a correct way to apply certain small signal input. So, of course, it will give you certain terms quite similar to this, quite similar to this one. So you can check it. But point is, if you implement it this way, how can you actually separate the part for taking the signal? Think about this one. Who generated this small signal V in? So usually, if you are working with a cell phone, then this small signal input is typically generated by your microphone, or sometimes if we are talking about the receiver part, then this small signal input is received from your RF antenna part. So it means that each of them have their own rule for operation. So if we just integrate or making this messed up situation, then it would be really important to make the first part or previous part and this amplifier part. So we have to separate them. So our basic assumption is, okay, this kind of mixed approach is not allowed yet. We have to think about there exists certain okay, so there exists certain small signal input quite much separated, well separated from our amplifier part. So are you with me? The situation is you have external environment. It generates signal, and we wanted to take it. So take to where? We wanted to take it to this part. Then how can it take it? That is my question. So now it says that, for example, some of you can say this way. Okay, so there exists the external voltage source which has the AC component. Why don't we just connect them? That's no way. You know that if we connect it in this way, it just dictates that your voltage here should be given by your V in itself. If it has no DC component, then this bias, this point is just biased very close to 0. No, you don't like it. Then maybe, okay, I understand. Then I will do it like this instead of this guy. Why don't you just introduce a certain DC bias condition, so which is happen to be equal to our V in DC? Then there will be no contradiction. But please note that it is once again exactly same with our previous one. Try to make the mixed combination of our DC bias condition and small signal input. They are messed up here, so we don't like it. So our goal is DC operation condition should be determined by our amplifier. Amplifier has its own right to determine its operation condition. In the same sense, voltage source has small signal voltage source has its own rule and its own requirement. So we cannot dictate that this bias value is exactly same with the one we wanted to have. So unfortunately, I mean that this is not the case. There will be certain V1, for example. Let's say that this is DC. And we have no way to control this V1. this V1 is just taken from our microphone or antenna, so we cannot change it. But still, we wanted to take this node voltage as some of a desirable DC input voltage plus V in, which is time dependent quantity. That is our problem in today's lecture. So are you all with me? Are you sharing the issue together with me? So it is always easy to say, okay, since we have a very beautiful voltage transfer curve here, then just changing our input signal, that will give us the perturbed output and takes this perturbed part as an output signal. That is easy. However, how can you actually implement it? How can we make a safe route for our DC bias voltage and small signal voltage? So that is the topic of today's lecture. So now it's like this. Now when you consider this node, let's just write down our desire. So we wanted to have both of DC and AC component. And what we wanted to have is here we have a DC component and AC small signal component. And in the case of DC, we wanted to use just this serially connected resistor network. Okay, we wanted to use this guy to provide our DC input. And in the case of AC, instead of that, we just wanted to take this guy shown here. So depending on frequency, so please note that depending on the frequency, we wanted to separate the path for voltage propagation. So in the case of DC, we wanted to use this route, and in the case of a small signal, time varying signal, we wanted to use this. This voltage should be copied into here in AC, time signal, time dependent signal, and DC should govern this route. Okay, so seemingly quite difficult. However, it can be achieved in an amazingly simple way. So let me just directly write down the solution for this problem. Okay, so are you all with me about this problem? So simply speaking, what we have to do to achieve this goal is just to introduce a capacitor C. So now the only difference between previous diagram and the current diagram is just existence of this capacitor C. Of course, we will discuss this circuit later in an intuitive way. However, for a while, just to try to solve this system with hand calculation. So, are you with me? So, let me just do it together with you. Okay. So, if we have to, okay, if we have to,
V1 DC가 뭔지 한번 더 설명해 주세요.
okay, this guy. Okay. I'm afraid my tablet is no longer working, unfortunately. Oh, this is really bad situation to me. So try later. And to your question, this is a certain unknown voltage. So think that this part is regarded as an external input to our amplifier, and we cannot determine the level for this DC level. So that's the reason why I introduce another symbol called V1. This is not in any sense this is not a universal symbol. So I just introduced this one. So its value is really arbitrary, depending on your certain circumstance. It can be either any value, take any value. So we don't want to take this value, interrupt this bias condition. So if this one is increases, and let's say that this one is still follow that increase and just increase from deviate from its optimal value. This is the worst case we want to avoid. So this input signal can have both of DC part and AC part, but we wanted to take only AC part of our signal. Okay, so that's the reason why I just introduce a symbol which should not be used in any sense. Okay. Okay, then let me just retry our tablet. Otherwise, we have to write it down in a blackboard, whiteboard, and I really wanted to avoid that situation. So let's just hope that everything works well. Oh, it works. Okay. Okay, so thank you for your nice question. So this is, once again, this is an arbitrary one, which really depends on the part for generating our input signal. So now let's try to solve this system. So we wanted to calculate this voltage, and later we will do a really intuitive approach to analyze this circuit. But instead of that, let's just apply our KCL to this output node. Then everything will be quite straightforward. Then how can I do that? So let's say that this is our V in. This one can contain both our DC signal and output signal, AC signal. And you know that here we have 3 branches. Which branches? There exists the first branch connecting this R2, and also there is another branch connecting R1, and finally there is another branch connected to the capacitor. So we have to say that the sum of branch current should vanish by the KCL. So let me just write down in this way. I will use this direction for each branch current. Yes, so please note that direction is important. So this selection of direction is really arbitrary. For example, I can write down in that way. It's anytime okay. However, point is, once you select your direction, then you should be consistent with that. Whether you will say that this is up or this is up, it's up to you. However, once you say this is up, then you have to be always consistent with this convention. So I wanted to say it this way. So in this convention, what is incoming flux and what is outgoing flux? So obviously, this guy is corresponding to outgoing flux, and these two are corresponding to incoming flux. So summing them all, we have to have equality. So, for example, simply speaking, V in T divided by R1 should be matched with what? Should be matched with the sum of R2 current and C current. So C current can be easily obtained. Oh, sorry, R2 current is quite easily obtained by VDD minus VDD minus our V in T. So that is divided by R2. So are you with me? This is corresponding to our branch current through R2 branch. Finally, we have to consider the capacitive current. Then how can you generate the capacitor current? Capacitor current is simply given by C times the time derivative of voltage difference. Then here we have voltage difference now. Then what will be the voltage difference? For this case, we have to take the voltage difference between this node and that node. And this node voltage is simply given by what? Simply given by our arbitrary V1 DC plus our variable signal V in and minus our V in. So sorry about that. I have messed up my symbols. Here we have V in, and here we have a small V in. But please don't be confused with these two components. So this is V in of our amplifier, and this is a small signal input, small signal our variable signal taken from microphone or antenna. Okay. So maybe you don't like it. Why don't you just change our symbol here instead of this in, which makes certain confusion, just to say that this is X. So this is an unknown one. This is our goal, and just to try to calculate this guy. Anyway, that will be quite straightforward to say. So now our goal is express our V sub X as a function of our circuit elements. So are you all with me? Then let's just do it. Here I have VDD. I will just expand our left hand side term, and VDD divided by R2. Good. Minus VX R2. It's good. And let's go to the capacitive part. This part is important. So when you go to the capacitive part, then you can find that first the time derivative of V1 DC component. And what will be the answer? DC component and its time derivative. This is just vanished. Okay? So thank you. So we will have just to C times the second term dV in dt minus C times dVx dt. That will be our case. Okay, so are you with me? I'm just expanding our case here. The left hand side is obtained from the incoming fluxes, and yes, this term does not contribute to anything because that is really DC. And we will have here once again the X R1. Okay, great. So let's think about this one. And here, if we just put it here, then we will have this one. V of x will have one over R1 and 1 over R2 generated from this part, and here we will have VDD R2, and finally we have some component. I put V in dt minus C Vx dt. So are you with me? If you have any question during my derivation, then please note that. Please interrupt me. So simply speaking, I'm just using one simple, really simple rule. DC value has 0 time derivation. So that is the only thing I have up to now. So then now let's think about this part. This part is simply obtained by what? So here we have, instead of that, we will have R1, R2 plus R1, R2, and just to multiply this part into there, then we will have R1, R2, R1, R2, R2, VDD, corresponding to the first term in the right hand side. You know that this these terms can be cancelled out. Yes. So we will have first the Vx. It has its own part, and it will have VDD multiplied by R1 divided by R1 plus R2. What is it? This is actually the DC component, DC input bias you wanted to have. Okay, that's great. Then now let's go to the second part. R2, R1, R2, and here we have a C and the V in T, C, V, X, D, T. So that will be the second part corresponding to this way. Okay. Okay, so you know now we have to introduce a certain. Up to now we have not used any difference between our DC component and AC component, and now we understand DC is corresponding to what? DC is corresponding to our DC component. And if we have a time varying signal, say this is, for example, sine or cosine, in this case, what will happen? Even after we take this time derivative, then that will give us still this component, and that will give us still time dependent quantity. Okay, let's think about one case where we have still DC component out of this time derivative. Then what happens to our input voltage? When we have constant dV in over dt, so if this is a time, this is a constant, it means that V in is monotonically increasing or monotonically decreasing. However, do you accept that kind of situation? You always assume that your signal T and your V in is given as DC component and certain signal taking any information here. So it's not like this. If your small signal is given as ever increasing value, then DC does not satisfy your your approximation. So this part is given as your So that will be one you have to have. So simply speaking, usually V in is given. You know, for example, V in is given as sine omega t or cosine omega t. Then after that, you will have what you have is just having one simple expression for Vx and dvx over dt. So this is just the first order expression. So once your V in is given, then you can get the value for this equation. This is the general situation we have to consider. Simply speaking, here we have capacitor and resistors. So capacitor introduce first order time derivative into our problem. So now we have, for example, here d over dt term. So now we will have first order ordinary differential equation. So that will be the solution of this partial ordinary differential equation will be the solution of our system. But point is here, the point that I wanted to say is here previously we had DC term here. It is generated from our external world and we wanted to avoid it. Then what was the result of introducing this capacitor? This capacitor, by action of this time derivative, it effectively blocking this DC signal. Whatever you have here as a DC form, this DC form cannot transfer to this node, Vx node. Whether you have increased it further 1 volt, no effect on it, or decrease it by amount of 1 volt, it does not affect your node voltage. So simply speaking, by introducing this capacitor, you just push back your DC component and only taking this V in term. So now you can understand, what you can understand is what you can understand is now this term will be still given as VDD and R1 and R2 R1, and here we have a time dependent term, and now it is certain that this term is not perturbed as V1 DC. That does not make any sense, any impact on our small signal, and there will be just dependence on our small signal input value. Of course you can say that then what is the coefficient for this V in? What is your opinion? What is the ideal case? The ideal case would be this coefficient is quite close to just number 1 unity. So simply speaking, the ideal case is by introducing this capacitor, you perfectly neglect or reject DC component and completely accept this small signal component. So that is what you wanted to have. Then how can you achieve this goal? What will be the capacitance of this capacitor C? Should it be large or small? Which is the condition for having the input signal almostly copied into this part. So I will, from now on, still we have 25 minutes, so we will discuss about this condition. So up to now, I just introduced KCL. Of course, you can solve this ordinary differential equation quite easily. But I wanted to say that just solving this equation is not sufficient. So please try to understand this situation. By introducing this capacitor, DC component is completely blocked. So that is the first. And now our question is, okay, I understand. How can we just copy our small signal input shown here into there? I will discuss this concept from now on. So, by the way, if you have any question, then please let me know. And of course, please try to expect your homework today. So what will be your homework today? So your homework will be, one of your homework will be just solving this ordinary differential equation, first order differential equation, when you have sinusoidal input signal. Of course, you can always rigorously solve it, but before solving it rigorously, just to try to understand it. Okay, now we are here. And DC component is solely given by this network. It is because we have introduced a capacitor, and this capacitor is used for separating our DC part from our input part. So it was quite successful. Then now question is, oh, I wanted to have V sub x, which is quite close to VDD R1 divided by R1 R2 plus here quite close to 1 times V in. Then how can we have this kind of situation? So I want to ask you whether all of you are familiar with the concept of impedance. So you have attended circuit theory. So if you don't have any exposure to the impedance, then please let me know. Then I will try to explain it again. So for example, if you are coming from physics concentration, then maybe you are not much familiar with this concept. So everybody know the concept of impedance? Okay, you are not. Okay, good. And anybody? Okay, I will just assume the zero base. So even if you are coming from ECS concentration, then please just listen my explanation once again and check whether your attendance. So simply speaking, it's like this. It is impedance is a generalized version of concept of resistance. So think about the resistance. If we have a resistor, we have V equal to I R. So seemingly it means that it is on instantaneous relation. So instantaneous voltage always directly affect instantaneous current with certain coefficient R. For example, there is nothing like that. For example, our T 1 second ago affect our I at right now. Can you expect such kind of behavior? So your past voltage is now affecting to the current in your current situation. It's not possible for your resistor. However, if we consider other circuit components like capacitor or inductor, that can happen. Your past value can affect to your current value in terms of terminal quantities. For example, let's think about this one. I over your capacitor is simply given by C times dV over dt. So you are also, let's just make a crude approximation about this time derivative. So let me just think about your current at a certain time t, and with a crude approximation you can, for example, make certain approximated quantity. Please have a look at this delta t. This is a small time difference, and v t minus v t minus delta t. Of course, if we have very small delta t difference, then maybe this is not that much bad. If we just take the limit of delta t is vanishing, then it becomes exact. This one is just a definition of a derivative. But still, even without this approximation or this limiting condition, we think that this is quite good for reasonably short time difference. So, simply speaking, I wanted to say that your current value at present time is really affected by your voltage value or delta t past, okay, delta t ago. So now you can say that your voltage and current are not immediately related. There can be certain delay between your terminal quantity and terminal voltage and terminal current. So that's the reason why this kind of simple relation like R is not sufficient to make the relation between V and I. So now in small signal sense, so our V and I, so sorry about that, instead of this large capital letter, I want to introduce small v and small I, showing that they are small signal and sinusoidal signal, and they can have different phases. So in order to make the relation between this and that quantity, we introduce a certain number z, and this one is called as impedance. And this impedance is just regarded as a generalized concept of your resistance. Of course, if your signal is just instantaneously mediated, for example, like a real resistor, then your impedance will contain only real part. So real part means that always your voltage and currents are in phase. They have same phase. For example, let's just consider this cosine omega t. If your voltage is cosine omega t, then your current will be obviously cosine omega t. So in the case of a resistor, so you will have the real, just multiplying certain number, you will have the form like this. But instead of that, let's think about another case. This is the R case. Now when you consider the capacitor, and let's say that your voltage is given as cosine omega t, then what will be your current? So since your current is proportional to time derivative of your voltage, you have to calculate the time derivative of your cosine omega t. Then how does it look like? It will give you just terms corresponding or proportional to minus omega times sine omega t. Certainly, yes, this guy and that guy are not in phase. when cosine is showing its maximum, then sine has its minimum value, not minimum, but its value is approaching to 0. And when sine shows its maximum value 1, then cosine becomes 0. So they are not in phase. Actually, their peaks are not matched when this one is goes down and other one is goes up. So in this case, in this purely out of phase case, then we can introduce the impedance corresponding to a purely imaginary one. So yes, so to most of you, you are quite much familiar with this concept and you have heard about that, but I just repeat this discussion once again because some of you are not familiar with it. So simply speaking, I just revisit once again about the impedance of your capacitor. Let me just do it together with me. Let me take it together with you. So let's see this one. Your I of t is now given as c times dv t and dt. Yes, this is the equation for your current in the case of capacitor. But when you think about this impedance, we wanted to treat it in a frequency domain instead of a time domain. So let's try to transform from this time domain to frequency domain. Then let's say that I will just introduce some quantity with tilde to say that this is frequency domain component. Okay. If you don't understand about this frequency domain transformation, then please let me know. Then I will just also have the C, because this is just a constant, no change even under this transformation. And finally, what will be this guy? If we assume certain angular frequency omega, then this dv over dt is simply transferred to what? Simply so manifest. So if you don't understand this transformation, then please let me know. So in the frequency domain, this d over dt is just transformed to j omega and their time frequency dependent term. Then from this one, please try to estimate the impedance. What was the impedance? Impedance is the relationship between voltage and current in a frequency domain, and their connecting coefficient is given as impedance. Then if we accept this form, then our voltage in a frequency domain is simply given by I in a frequency domain multiplied by 1 over j omega c. Are you with me? So I want to say this guy is corresponding to what? Corresponding to your impedance of your capacitor. This is simply given by 1 over j omega c. What is it? So let me just go to the two different limiting cases, like extremely low case and extremely high frequency case. Then please think about your impedance, capacitance's impedance. If omega becomes infinitesimally small, it means that you are working with a low frequency condition. Then what will happen? In a low frequency, then once or first of all we have to say that fixed C is just a given number, and when you go to the almost close to DC case, then this omega term goes quite small, and now your capacitor impedance becomes almost infinitely large. On the other hand, if we go to high frequency, then what will happen? If we go to high frequency, then this term becomes quite large, and you will have almost zero impedance. So let's and please note that impedance is a generalized version of our resistance. Then let's coming back to this guy. Here we have once again DC component, and this here we have time dependent AC component. So in this case, this DC component can be regarded as a limiting case where omega becomes 0, and it has non-zero omega case. Then what will happen? Although we have here single capacitor C, but depending on their frequency, this C can be seen as two different impedance values. From the viewpoint of your DC component, what happens? If you are working at DC, then DC at DC case, your capacitor will be working as infinitely high impedance here. So simply speaking, from the viewpoint of your DC component, this guy means that this capacitor is just infinitely high blocking part for your signal transfer. So that's the reason why we cannot have any kind of voltage copying from this left hand side to the output. But instead of that, that was already discussed in our previous discussion. Now point is the AC part. Now we have a non-zero frequency, and what happened? In this case, in AC case, its impedance is simply given by J omega C here. So are you with me? Then let's say that this omega is a given number. Yes. For example, if you are working with 1 kilohertz, then your omega will be 2 pi times 10 to the 3 per second. So if you are working at 1 kilohertz, if you are working at 1 megahertz, then obviously that will be 10 to the 6. You can understand. Let's say that you have a fixed operational frequency. So can you just fix your operation frequency? Yes, you can. Why? If you are working with your microphone, then your signal is voice signal, and then your voice signal has well-defined bandwidth. You cannot generate a super high note, or you cannot make a very low note. So since we are all human beings, the frequency we can generate by voice is fixed. So we can say that if this application is microphone, then we can assume that generated signal is within certain frequency range. Also think about cell phone. If you are working with a certain cell phone, then that cell phone has well assigned frequency domain for your RF communication. So you have well defined frequency. You can always assume that your frequency is in a range of a certain part. Yes, so you can fix it. Then how can we make now this impedance so small when you have a fixed omega? Simple rule is just increase your capacitor. If you have higher capacitance at a given omega, given frequency, then its impedance will decrease. So let me just finalize our discussion. So if you have sufficiently large capacitance, then what will happen from the viewpoint of your AC signal? Then I will just draw it from now. It will just look like this. Here we have, I will just take into account only small signal quantities, and here we have a capacitor, and here we have a resistor, which is R1, and please concentrate here. Here we have a R2, and that is also grounded. What? So we obviously R2 is connected to VDD, but I just drawn ground. What's wrong? In this case, I told you that I will consider only AC related component. So here ground is not actual real ground, but it should be regarded as ground in AC sense. Okay, VDD, it has only DC component and no AC voltage perturbation is allowed. So that's the reason why previously that was VDD in its correct form. However, if we just consider AC signal only, then this DC voltage VDD can be regarded as AC ground. So are you with me? I mean that here we have now impedance is corresponding to 1 over j omega c, and now our final question is, then what is Vx now? Or it's yes, time dependent quantity, frequency domain quantity. How can we calculate it? Then now we have both route to the AC ground. For example, R1, R2. From this X node, Vx node, we have two passes, R1 and R2, and they are parallel. Then what will happen? This signal, this circuit diagram can be simplified as what? Simplified as just parallel equivalent resistance of R1 and R2. Then finally, I wanted to say that in this sense, your Vx frequency domain component of your Vx is simply given by now V in multiplied by certain voltage division rule, just following the resistor way. So R1 parallel R2 plus 1 over j omega c. This is just serially connected impedances, and also R1 parallel R2. That will be the expression for your X node voltage. So finally, what happens if you have sufficiently high capacitances? So for example, let's say that your capacitance is so high, therefore the product omega c is sufficiently larger than 1, much larger than 1. Then what will happen? You can safely neglect this contribution, yes, and only we have equivalent resistors R1 parallel R2. So in that case, this ratio becomes just 1. So now you have just your input signal is sufficiently well copied into your X node. X node is the input node, the gate voltage of your amplifier core. So with this introduction of a simple capacitor, sufficiently large capacitance, then you can achieve both purpose. You can provide the DC value, DC operation value, well separated from your input signal, and taking only AC signal, and in this case only AC signal sent from the external world is almost exactly here, quite close to unity, copied into your input signal. That is the way you proceed with this amplifier. Okay, unfortunately time is up, so I will wrap up today's lecture. And today we have introduced the concept of impedance, or review the concept of impedance. If you are not very familiar with this one, then please review the concept of impedance, and I will give you some related homework. Thank you, and see you next Monday in this class. Bye.